Hello and welcome. My name is Partho Majumdar. In this video, we will discuss about support vector machines. This is one of the algorithms which we can use for regression, and we will see how this algorithm can be better than linear regression. Support vector machines, or SVMs, were originally developed for solving classification problems. They are still used for solving classification problems, and they are very effective. It was much later it was realized that SVMs can also be utilized for solving regression problems. It was first proposed by Smola in 1996 and later developed by Drucker in 1997. The main motivation behind using SVMs for solving regression problems is that it minimizes the impact of outliers on the regression equation. We will see soon how the outliers can impact the regression equation, whether it is a linear regression or whether it's any other form of regression. We will discuss one form of using SVMs for regression problems, that is epsilon insensitive regression. There are other forms also. However, this form of using epsilon insensitive regression in SVMs is the most popular. Now let us discuss the problem of outliers when it comes to regression. Let us consider a problem that we have got one independent variable and one dependent variable. So we are trying to estimate, let's say, the dependent variable y for the independent variable x. So for this, this is going to be easy on two variables to visualize the problem. Now supposing we have plotted that the x and y have these observations which we have gathered. So these are the observations which we have gathered. Now if we are doing linear regression, for example, through these observations, then we may say that we may try to draw a line through these points that we have gathered, and let's say we get this particular line. Now this is our regression line. We know that we will use the method of least square. So for method of least square, we try to figure out the distance from the actual value and the predicted value and see what is the least amount we can get in terms of these error terms. That is, these are the error terms, and when we take the error terms, we square it and then we sum all the error terms and find the mean of these error terms, and we try to minimize this. So this is known as the mean square error. So we try to minimize the mean square error, and the line which gives us the minimum mean square error, we consider that as our regression line. Now the problem what occurs is that supposing we have an outlier, supposing we have some points here. Now these outliers, what they will tend to do is that when we have outliers and then we were going to take the mean square error, then what will happen is that this line will get pushed slightly upwards because of these outliers. Now our linear regression equation will be affected because of these outliers, because it will give a result of linear regression which will be slightly biased towards these outliers. Now this is the problem which we have with outliers when it comes to linear regression. We will see next how SVMs can solve this problem. To solve the problem of outliers, first there came a solution in the form of Hoover function. Now Hoover function, what it did was that instead of taking the square of the residuals, it took the absolute value. So if you try to plot the residuals are the actual value minus the predicted value. So if I'm going to use the mean square error, the square of the residuals will form a graph like this. We know that because this is going to be parabolic because we are taking the square. Now instead of taking the square, if I take the absolute value, first of all the range of values will become much smaller, and then the absolute value of errors will be something like this. So this in a way will solve the problem of outliers to the extent that the outliers will have less impact on the linear regression equation. What support vector machines does is that it takes a value of epsilon. It takes this value of epsilon, and this epsilon can be set by the user. Now when this epsilon is set, supposing we have a relation between two variables like this, and we try to figure out a line through these ones like this, then I take a epsilon such that if the residual is greater than epsilon, only then I will consider that residual for forming an impact on my regression line. So if I I will make a boundary like this around my residual line and say that anyone who is outside this boundary can only impact my residual line. So I will take a epsilon such that the residuals which are going to be smaller than this epsilon value will not be considered for contributing to my linear regression equation. Second thing is that for the residuals which are larger than epsilon, we take the absolute value and we do not take the square value like we do in normal linear regression. So by doing that, they contribute in a linear manner to the regression equation. So the impact of the outliers is thus minimized. So we can summarize that the impact of the SVM approach is that large outliers have minimum impact on the regression equation. This is because, like we discussed, we do not take the squared residuals, instead we take the absolute value of the residuals. Second thing is that samples which have small residuals, they will have no impact because the samples where the residuals fall within epsilon, they will not be considered in the regression equation at all. So that is the impact of the SVM approach. Now, just to recall, in this context, in the linear regression when we discussed, we know that the cost function that we considered was that we take the y pred, that is the predicted y, minus the actual value of y, square it and sum up all these terms. This is the residual basically. This is our residual. This is the residual. So we take the residual and square them and then sum up all of that and then take the mean of that. So this is the mean square error. So you can take, if you do not consider this mean, you can also take it as the sum of the squared error. So, or if you take the square root of this becomes a root mean square error. So root mean square error. So either of these terms, mean square error or root mean square error or square of sum of square of errors, we can minimize to get our linear regression equation. So we will use this knowledge in our next discussion, that is the cost function of the SVM. Now in SVM, the cost function we consider is that, first of all, we take a value called C. This is the cost penalty we put on the residuals which are very large. So this value can be set by the users. Then we take the mean of a function which is the epsilon insensitive function, L epsilon let's call it, of the residual. So we subject the residual to a function called L epsilon, which is the epsilon insensitive function. And then we add the beta, sum of the beta squares. Now beta squares, beta is nothing but the coefficients of each of the independent variables. So this is our cost function. Now one thing should be clear from here is that there are parameters that we can set. Is one is I can set the parameter for the cost function is SVM. That is, if how much a penalty I would like to give for the large residuals. And second thing is that it will become clear soon that in this epsilon insensitive function, I can set the value of epsilon. So I can set the value of epsilon to be small, large, and based on that, the SVM will behave differently. The regression equation that we get from SVM is as follows. We get the f of u. U is the value which we want to predict, the new data which we get for this data we want to predict the value. So this is equal to beta 0 plus summation of alpha I into k of xi u. Now u is the value which we're trying to predict and xi are the previous values which we have got in our data set. Now here alpha I is a unknown parameter that SVM considers. This parameter determines the way the SVM will calculate our future value. Now these parameters are optimized by SVM by the epsilon insensitive function. Now here this function k is very important. This is the kernel which we can use for SVM. Now SVM allows for utilization of various type of kernels. The simplest kernel is a linear function. I can use a linear function, or I can use a polynomial function, or I can use a radial basis function. This is basically a exponential function, or I can use a hyperbolic tangent function. This is tan h. So basically I can use a linear function or a quadratic or cubic function, that is polynomial. Then I can use the exponential function, which is the radial basis function, or I can use tan h for a hyperbolic function. So now what becomes clear is that when we are implementing SVM, we can parameterize, or you can use these hyperparameters. I can set the value of epsilon, and I can tune my SVM model, or I can set the value of C and check whether my model becomes better or worse, and I can use different kernel functions to see which kernel function fits my data the best. Normal technique is that we use a kernel function. Normally we will use RBF, that is the exponential function, while using, this is the default as well for SVM, that is we use the exponential function. Then we set epsilon to a small value. This takes a little bit of time for experimentation, but however, normally it comes into a value between 0.01 to round about 0.9. So we normally set this, but this depends on the data. You have to do some experimentation to find the right value of epsilon. And then after we have set these two parameters, that is the kernel function and the value of epsilon, we keep on changing the value of the cost penalty which we will subject for the large residuals to come to the most optimum model of SVM.